Okay, today I'm going to introduce proof to you. So let's start with a definition. This is my definition of what a proof is. It's an argument that uses deductive reasoning to show a conclusion is true. We talked about the difference between deductive and inductive reasoning about a week ago, and you guys have been using a combination. You've been practicing conditional statements, but mostly inductive reasoning. If you can't come up with a counterexample, then we just say a statement is true. Well, there's a better way to say a statement is true, and that's to prove it's true. So we're going to use a series of statements that can be justified by properties, definitions, postulates, and or previously proven statements, which we will be calling theorems in this class. And that series of logic statements, which we can read as if-then statements, is going to get us from knowing one thing is true to actually convincing somebody with 100% certainty that something else has to be true based on what we started with. So let's get started. We're going to actually go back to something that you guys are very familiar with, solving an algebraic problem. And we're going to turn this into a proof. And I know you did this at some point last year, but maybe didn't set it up quite the same way. So the way we're going to set this up is we're going to make two columns. And we're going to solve the algebra problem on the left-hand side. I'm going to put the words statements at the top. And if you could do this on your paper as well, this will be a great example for you to go back to. And then on the right-hand side, I'm putting the word reasons. And that right-hand side has to be our postulates, properties, definitions. Those are the only things we're allowed to use as reasons. Because remember, we're doing deductive reasoning. We have to use known true facts in order to convince the reader that what we're saying is true. The first step, and I am going to go ahead and number these, so I'm going to number my steps on the left side. And I know you don't normally do that when you're solving an algebra problem. That's so that I can match it up with a reason on the right side, and it makes it a little bit easier for somebody to try to follow. So my first reason is going to be given information. We had to start with something, so that's the problem that you were given. Done. Move on. Okay, so how do I solve this problem? Now just think about if you're in algebra class, what would be the first thing you would do? Some of you may be thinking distribute. I'm going to try to get rid of the 1/2 because I don't like fractions. So I'm going to say, what if I multiply this by 2 on the left side? And then that, of course, means I'm going to multiply by 2 on the right side. So we don't normally write that when we're doing a proof, but we think that. So we're going to, I'm just going to write it for now, but know that in the next problem, the red isn't going to be there. It's just going to be a series of statements. So what we have on the left side is the 2 and the 1/2 cancel out. So I have 3x plus 12 is equal to 2 times the quantity 5x minus 8. I know I didn't multiply it through yet. Please make sure you write it exactly as I'm writing it, because if you multiplied it through, then you distribute it. But I can't do 2 steps at once. I've got to make this really clear for my reader. And I already used a property there by multiplying by 2 on both sides. I used my multiplication property of equality. And you can write out multiplication property of equality or use MPO for short. Now I am going to go ahead and do what you are all wanting me to do, which is distribute, which means the left side is going to stay the exact same, and the right side is going to become 10x minus 16 when I distribute. So that's my distributive property. I don't think I can put depot there because that would mean division. I should have stated up here, I'm going to go back slightly to my step 2. You could have said that you are dividing by 1/2. So technically we could say depot there. That'd be the same thing as multiplying by 2. And some people like to think of it that way. You've got some options here for step 4. Basically, we need to get our x's on one side, numbers on the other side, so this is entirely up to you. I'm going to go ahead and move my x term first. So I'm going to subtract 3x. Again, what's in red would not normally appear in a proof. So I'm going to have 12 on the left is equal to 7x minus 16, and I use my subtraction property of equality. I'm going to need some more steps. You could certainly add. So from here, I'm going to move my 16 over, and I know some of you have already solved this problem. That's great. So I'm going to add 16. and I'm going to have 28 is equal to 7x. Addition property of equality, again, step 4. We could have said that when we got to SPO, I meant to point this out, we could have said that we added a negative 3x right here. And we could have said that we used APO instead of SPO. So but most of us like to think of it as subtracting. I'm going to keep going, a little more room. So let's add step 6, I'm close. Step 6 is going to be division property of equality, because I'm going to divide by 7 on both sides, and I'm going to get 4 equals x. Please look at how you wrote that. Make sure you actually wrote 4 equals x and not x equals 4, because we're tempted to do that, and we're used to doing that in algebra class. But my division property of equality only says that I can divide both sides by the same number. That's what I did. I divided by 7 and divided by 7. So I know you want us to say x equals 4, and I'm going to do that, and then I'm going to ask you, what property did you just use to say, if 4 equals x, then x equals 4? And you should be thinking symmetric. Property of equality. Okay, I said that we can read these as conditional statements, and this will become more important next week. But what we can do with our proof, now that we're done, or even as we're going along, is we can literally take any one of these and say, if we know line 1 is true, then we can conclude line 2 here because of my multiplication property of equality. And then I can go from line 2 and say, okay, if I know line 2 is true, then line 3 follows, 3x plus 12 equals 10x minus 16. And how do I know that? Because of my distributive property. And these basically are a series of conditional statements where the hypothesis turns into the hypothesis leads to a conclusion, and that conclusion turns into a hypothesis that leads to some other conclusion until we finally solve for x. Okay, that's the gist of an algebra problem. You just never knew that you were doing a mathematical proof when you were solving an algebra problem. We're going to try a second one here, except this one, I already have the proof written out for you. And this time you're just figuring out what happened from one to the next. So why don't you go ahead and give this one a try, and then we'll do a check. Okay, hopefully you paused the video and tried that. I'm going to talk you through what you should have gotten. I'm going to read this one as conditional statements. So I'm thinking to myself, if I know 3x plus 5 divided by 2 is equal to 7, then I can say 3x plus 5 equals 14. First reason, I'm given my starting equation, and now I'm trying to prove that 3x plus 5 is equal to 14. What happened? Well, it looks to me like we multiplied by 2 here because the 2 is gone from the denominator. Does it work on the other side? If I multiply by 2, indeed it does. I'm getting 14. So I'm going to say that that is my multiplication property of equality. Okay, now I'm back to the left side, and I'm now making this my if, my second line. Then the third line follows that 3x is equal to 9. It looks like I got rid of the 5, but how did I get rid of the 5? I subtracted 5 from both sides, which is giving me SPO. Or, if you wanted to, you could say APO, because we could always say that we're adding a negative 5. If 3x is equal to 9, then x is equal to 3, and I think you're seeing that one. Depot. I'm finished. I would be told sometimes what I'm supposed to prove. In this case, that's the last step. I don't need to use symmetric property here. We do like to do sometimes a closure on our proof, and we'll put the letters QED, which is an abbreviation from Latin words that mean this is done. So sometimes we do that just as our signing off. I'm done, and I'm signing off of this video. You now know what a proof looks like. We're going to use this same structure, and we are going to stop doing algebra, and we're going to go actually start proving geometric conjectures. So you have a nice list of conjectures, and you're going to look at how can you actually verify that what you think is true really is true using a series of logic statements with justifiable reasons that we know are true to lead from one given piece of information to a miraculous conclusion.